starting the recording, so it would be great if one of you can remind me. Okay, so now the meeting is being recorded. Okay, so now, as I was saying, so initially in the very early days, computers were just like, say, calculators, where there used to be only one task being processed at a time. So the whole memory, it had a very simple operating system and one task. So as long as that task is running, the other tasks have to wait. Then people realized that most of the time is being spent in IO, input output. And that is because input output devices work much slower than a CPU. And this was true even during those times, say 40 years back, that input output happens much slower than, say, processing on a CPU. So then people started thinking that why should other jobs have to wait while one job is doing an IO? Instead, can we do this, that when one job is doing IO, some other job can use the CPU? So that led to approaches like spooling, which we were discussing. So here, if you see this diagram, so there's a spool buffer. Now spool buffer may not be so in this diagram it seems it's a different device, but it may not be so. So logically it's a spool buffer, but it may well be a part of the disk even. Okay. But basically there is this spool buffer where the CPU writes data. So suppose the data that is to be output, the CPU writes here. And then the rest will be handled by the IO processor. So the IO processor can actually take data from this spool buffer and get it output. Or the IO processor can take data from input device and store it in this spool buffer. So the CPU does not have to be involved in this part. So suppose one process or one task asks for IO, then CPU can write that data to the spool buffer, and then the rest of the job, IO job, will be handled by the IO processor. Meanwhile, the CPU can be assigned to some other task. Okay. So at that point, what happened is this. So an IO processor, so even though spooling was quite early, but it still brings in some important concepts. So one concept is the addition of IO processors, which leads to this, that the IO of one job can be overlapped with computation of other jobs. So when IO processor is handling the IO for one job, the CPU can be assigned to some other job. And this in turn leads to better utilization of the CPU. Also, there are some other things to note. With spooling came this concept of virtual device. We will discuss this more in the course, but still understand that, going back to this picture, for the CPU, the spool buffer is kind of a virtual device. In that, the CPU thinks I am outputting to the device, fine, but actually some other mechanism happens from so that data from that virtual device is actually sent to the physical device, say the printer. Or data read through the actual physical device is stored temporarily in that virtual device. So the CPU can only think I am reading from this spool buffer. Okay, so from the perspective of the CPU, the spool buffer acts like a virtual device. Right, so this was an early advancement, which has already, of course, been much developed in the later years. But this was the first time kind of the concept of virtual device came. Also, another important landmark here is that, remember what we discussed earlier, there only one job used to reside in the memory at one point of time, and all other jobs had to wait until this job was finished. But now notice that we are seeing multiple jobs being simultaneously residing in the memory, and CPU to be allocated to one of them at a time. So if one, so say simplistically, there are say two jobs in the memory, A and B, so that when A is doing IO, B can be assigned the CPU. Right? So multiple jobs are residing in the memory, which was not the case earlier. So again, see, this is why we are discussing the history. The different advancements are telling you the different requirements for building a modern system today. Right, so the concept of virtual device, concept of multiple jobs simultaneously residing in the memory, concept of I/O processors, all these will help us in building modern systems. And the final concept that I would just like to say is CPU bound and I/O bound jobs. Okay, so basically, what does these names indicate? Just intuitively, what do you think they indicate? What does CPU bound and I/O bound jobs mean? The names are quite indicative. That's why I'm asking. What do you think they mean? Yes, so what Abhishek is saying is correct. So typically, you might think that there are some jobs which would require much more CPU time and some other jobs which would require much more I/O time. So think of a job which reads in a lot of data from the memory, from the disk. Maybe reads in a huge array and then just computes the sum, or reads in a huge array, or a matrix, and then just computes the sum of some elements in the array and then again writes back that array. So this kind of a task requires a huge amount of input and output, but the processing is possibly not that much. On the other hand, there can be some tasks which do not need to read in much data, but they need to do a lot of operations. And I'm sure you have written both kinds of programs in the 3 years that you have spent here in IT. So you get the idea that some jobs would be more closely bound to the CPU. They would require CPU time much more, whereas some jobs would be bound to the I/O more. So now let me ask, which kind of jobs do you think is necessary for, say, a scheme like spooling to work? CPU bound jobs should be more, or I/O bound jobs should be more? Which kind of job do you think, having which kind of job is more preferable for a scheme like spooling? Okay, Dhrubil says CPU bound. Any other answers? Okay, so one to one tie. Okay, I/O bound jobs are winning. Okay, good. So which? I'm not sure if your name is which or what, but okay, D which.
Yes, sir, it's which.
Which, okay. Actually, which has given the right answer. It requires a good mix of I/O bound and CPU bound jobs. Because see, if you have only I/O bound jobs, then the whole advantage of spooling is lost. Because say all jobs are I/O bound. So then they have to wait for each other. Because we are assuming that only one job can do I/O at one point of time. On the other hand, if all jobs are CPU bound, then again, I mean, there is no extra advantage we gain by giving an I/O processor, etc. So for a scheme like spooling to work well or efficiently, it needs a good mix of CPU bound and I/O bound jobs. So that when the I/O bound jobs are doing I/O, the CPU bound jobs can utilize the CPU and work. Okay. So basically a good balance is needed. Whether we have that or not, that's a different issue. I'm just coming to that. But what would be preferable is to have a CPU bound and I/O bound job in good balance. Okay. Yes, Dhrubil says most CPU bound jobs take less time compared to I/O bound jobs. True. But if, as I said, if all jobs are CPU bound jobs, then are we getting any advantage by adding things like I/O processor, spool buffer, etc.? And besides, that's not a practical scenario that you will get all CPU bound jobs. It will happen that some jobs will require a lot of IO, and therefore a good balance is needed. So it's true that CPU bound jobs may take less time, like total time. They will take more CPU time, but total time, if you think, then yes, CPU bound jobs are likely to take less total time compared to IO bound jobs. But it is not a practical scenario to have all CPU bound jobs. And besides, as I said, see, if that was the case, that most, say 99% jobs are CPU bound, then we did not need spool buffer, IO processors, etc. Because maybe only 1 or 2 jobs will require IO, so maybe they can wait. But that's not the case, right? Often it is a mixture, and schemes like spooling are designed thinking that there will be a good mixture of IO bound jobs and CPU bound jobs. Now, again, that is not the case today. We will come to that, but the schemes like spooling are designed assuming that there will be a good mix of IO bound jobs and CPU bound jobs. Let's proceed. Now, spooling is a special form of what we call multi-programming. Okay, spooling is a special form of multi-programming. So let us understand what multi-programming is. This is kind of the another stage in computing systems. The first one was batch processing systems, where only one job used to be loaded in memory and every other job has to wait until that finishes. The second stage, you might think, the second logical stage came as multi-programming. Spooling was a special case of that. So what is multi-programming? Multiple jobs are loaded into the memory at the same time. And there is a concept of a job scheduler which selects one job for allocation of the CPU. Okay. So suppose job scheduler has selected a job A that is currently running on the CPU. Now a big IO request has come from A. Then it is understood that A cannot proceed right now until this IO is completed. So what is done? Ideally, A should be doing the IO using the IO processors, etc. Whereas the CPU should be allocated to another process B or another job B. But there is an important requirement here. At some point, A will have to be resumed. So then the system should not forget till when A executed. Therefore, A's context needs to be stored. So suppose A has already done some operations, right? It has some, so the variables of A, they have some value currently. The system cannot simply forget them, right? Because A has to be resumed from that point where it was left off, as in IO request came, so A was removed from the CPU, but then the system cannot forget the stage at which A was, because A cannot start from scratch again. A has to continue from this point. So there is a concept of A's context being stored. Right, so that is what happens. If a big IO request comes from job A, A's context is stored and another job B is started. Once A's IO is finished, the CPU comes to know. That happens because, say, the IO processor will give some indication to the CPU. So once A's IO is finished, then at some point A will be restored. Okay. So this is multi-programming. As you understand, spooling is a special case of multi-programming. So we are essentially discussing the same concept. Now, there are some issues which come with multi-programming. So some things have to be handled. As I said, we have to rely on the fact that job B can execute on the CPU when job A is doing IO. So it has some necessary conditions. One is the need to store context. So there has to be a mechanism by which A's context can be stored while the CPU is allocated to B, so that A can resume at some future point of time. This was not these requirements were not there in a batch processing system, where only one job used to be executed till its completion. But now, see, so we want the systems to be more efficient, but for that some additional complexities also need to be handled. One of them is this, that you need to store context. Next, think about it. Memory protection. Why do you think? Okay, so again, let me ask a question. Why do you think memory protection is needed? Or what is this even about? Just intuitively, any idea? Think about a major difference between batch processing systems and multi-programming. Compared to, with respect to the memory. Okay, think about a major difference between batch processing systems and multi-programming with respect to the memory. Why do you think we are talking about something called memory protection? Exactly. So Roshan and Srihas have given the right answers. In a batch processing system, let me just show you that picture once more if you have forgotten. This was a batch processing system. Can you see? So the whole memory had only just OS. The OS will always remain in the memory at some point, at some part. But the whole memory was given to one user program. But now we are talking about things like, let me go back to that multi-programming slide. Yeah. Now we are talking about multiple jobs being loaded in the memory simultaneously. So clearly, one job should not be allowed to access the memory of another job. Right, so now we are getting the picture that the memory will be divided into many portions. The OS will be occupying one portion, but other portions will be assigned to different jobs. So clearly one job should not be allowed to hamper or to change the memory of another job. So some sort of memory protection is needed. Okay. Also, there is something called another thing which is needed is a privileged mode. So for example, let's say this thing that stored the context of one job and allocate the CPU to some other job. Who should be able to do this? Should any job be able to do this? Possibly not. Then what if some malicious person writes a program which simply only allocates the CPU to itself? Right, it saves all other jobs and only allocates the CPU to itself. So that should not be the case. Only there should be kind of an administrator. Right, so I think we understand that in any system, normal users and administrators are not the same. Someone should have a higher privileges to ensure that the system is running properly. So that is something called a privileged mode. So usually the operating system will work in a privileged mode, whereas the other systems will work in maybe user mode or something. Right, so all these requirements are coming in because now we are trying to make the system more efficient. We are trying to load multiple jobs into the memory simultaneously, and we are trying to allocate the CPU to different jobs at the same time, at different times. So all these requirements are coming. So these are costs that we are paying, more complexity, but we are hopefully getting more efficient as a more efficient system. Now, the last point we have discussed already. So for multi-programming to work well, we need a good mix of CPU bound and IO bound jobs. Right? So that was the assumption in the days of multi-programming. So see, we have discussed two stages, batch processing and multi-programming. But then people again after some years, people understood that a good mix of CPU bound and IO bound jobs may not be always practical. Maybe that CPU bound jobs are much more, or IO bound jobs are more, whatever. And this cannot be ensured always. So then multi-programming does not work very well. So then came the third stage of systems, which is called multitasking. So instead of multi-programming, it's called multitasking. What is that? This, a logical extension of multi-programming, of course. CPU switches jobs so fast that users can interact with each job while it is running. And this gives the illusion of interactive computing. Example, the GUI or cancelling an ongoing download. So you might remember there was a question last week, maybe in the second or third class, that what about the GUI? We are seeing the GUI always. That means, does that mean that the program which is showing us the GUI is always running? Similarly, you can think of an ongoing download. Nowadays, we are actually shown that 30% download is completed, 32% completed, 34% completed, and so on. And at some point, you can even cancel an ongoing download. So what does this mean? Is the download program always running? So now think about it. I mean, there is a misnomer here. If that is the case, then think about it. The GUI is also always running. The download is also always running. How can that be? You have just one processor. So two programs cannot be running always. So the truth is that none of these programs are actually always running. However, this is the illusion. The CPU creates this illusion. The CPU and OS together. The CPU switches jobs so fast that users can interact with each job while it's running. So again, going back to that chess tournament analogy, just once more. So there we were discussing how can Viswanathan Anand play 50 students? Because he can switch from one student to another so fast that every student feels that he is the only one playing with Anand. Similarly, CPU can switch the jobs so fast that every job or every user can feel that the CPU is only dedicated to him or her, and they can actually interact with the program. So this is the logical extension of multiprogramming. So now let me ask one critical question, which I want all of you to understand. With respect to the switching jobs, what is the primary difference between multiprogramming, which we discussed earlier, and multitasking, which we are discussing now? With respect to the switching of jobs, what is the critical difference between multiprogramming and multitasking? Any answers? Exactly. So Shubham and Somnath have given the correct answers. So in multiprogramming, remember we were saying that the job will be switched only when program is requesting an IO. But here in multitasking, we are not saying that. We are saying the CPU will decide sometimes when to switch jobs. That part is still here. When a program will request for IO, it will be switched. But even if a program does not ask for IO, the CPU or OS can decide to switch it, because the time has to be shared among many different programs, so that every program can feel that it is the only one running on the CPU. Right? So again, this is an important point which I want all of you to understand, so I'm repeating it. In multiprogramming, switching only occurred when a process asked for IO. So that's why if all jobs were CPU bound, then no one would be asking for IO and no switching would occur possibly. But in multitasking or time sharing, oh by the way, multitasking is also called time sharing because of this reason. We are deciding to share the time. So like if there are 100 jobs, every second will be divided into 100 units, and one unit will be given to every job, let's say. So then even if a job does not ask for IO, it can be switched. So our processor CPU can be taken away from that job and given to some other job. So that's a major difference between multiprogramming and multitasking. Okay. And that is why multitasking does not depend upon a good mix of IO bound and CPU bound jobs. This is the reason, right? So even if all jobs are CPU bound, still the CPU will time share. as in share the time among all those jobs. And of course, if there are some jobs which are waiting for IO, then of course it will be switched out and some other job will be allocated to the CPU. Okay. So now that we have moved on to time sharing, the characteristics of time sharing is, of course, it is a much more complicated system, which we will understand over the whole of the semester. But the advantages we get is we can work in real time. So actually we can meet deadlines for jobs. You may have heard of something called real-time operating systems. We are not going to discuss that here, but if ever you take a course on say real-time operating system, then you understand that strict guarantees can be given that this job will be completed by so and so time once it is issued. Okay. Similarly, this kind of a system is complex, but it leads to much better sharing of resources between jobs. So that is the advantage we are getting. But of course, we have to give a cost, that is the program, we have to give several costs for getting these advantages. Right. So some of the costs actually is mentioned in this next slide. So what does it need to, have this concept of CPU scheduling like this, time sharing? First, you need hardware timers. A hardware timer will, as I said, let's say that there are 100 jobs, so every second will be divided into 100 units. So someone should keep track of this. So say we are talking about 10 milliseconds, right? 1 second divided into 100 units, 10 milliseconds is each unit. So after one job has executed for 10 milliseconds, someone should arrange that this job is switched out and another job is allocated to CPU. So someone should keep track of time. So you need hardware timers. Okay. By the way, so again, let me ask a question here. Why? So suppose at this point, in this context, why cannot the OS keep track of time? Why do you need another hardware device? Why cannot the OS keep track of time? So say job A is running. After 10 milliseconds, job B has to be allocated to CPU. Why cannot OS keep track of time? Exactly, again, Somnath and Srihash have given the correct answer. The OS is not running now. Job A is running. So how can the OS keep track of time? Remember, there is only one processor. If job A is running, that means the OS is not running, or the kernel is not running. So if the kernel is not running, how can it keep track of time? Then the kernel would need to run always, right? So that's why when job A is running, the kernel is not running, it cannot keep track of time. There has to be a separate device, a hardware timer, which keeps track of time. And there will be some mechanism that when this time quantum is over, like say 10 milliseconds in our example, when this time quantum is over, that hardware timer will inform the kernel, now you need to switch. You need to switch the CPU to some other job. Then the kernel wakes up and does the switching. Okay. So again, this is a very critical point. So I'm repeating several times maybe. Job A is running. It has run for its time quantum. Then the timer is keeping track of time. There will be some mechanism by which the timer informs that this time quantum is over. Then the OS will start running, or the kernel will start running. Any idea what that mechanism would be based on what we have been discussing in the last couple of classes? So how can the hardware timer, what can the hardware timer do so that the process is switched actually? So process job A is running. Exactly, good. Again, Srihash and Abhishek, good answer. Yeah, also Shiba, Dhrumil. So you are getting the idea. So the hardware will generate this hardware timer will now generate some interrupt. And when an interrupt occurs, the kernel wakes up. So now the kernel will understand that the kernel knows which interrupt came. So if it is the hardware timer interrupting, That means the current process has run for its quantum. Now it has to be switched and some other process has to be started. Okay. Okay. Abhishek is asking, what does running of a job mean here? Basically, the CPU is allocated to that job. So very technically, running a job is running means, or a job A is running means, at this point, the CPU is executing the instructions of job A. So the CPU is allocated to job A. Okay. So job A is running means the CPU is allocated to job A. It has run for its time quantum. But now suddenly the OS cannot start. Someone will have to wake up the OS because the OS is not running now. Who does that? The hardware timer through an interrupt. When that interrupt comes, OS wakes up or kernel wakes up, saves the context of job A and allocates the CPU to some other job, say B. So now B starts running. Okay, that is how the switching from one device to another, switching from one job to another occurs. Okay. Any other questions here? Okay, let me proceed. If you have questions, write it here. Okay, Ishan says, just does context mean register contents? Yes. It means some other things also, but yes. From your core knowledge, you will understand that when one program is running, it has different values written in different registers, etc. So yes, saving the context actually means saving those register contents. There will be some other things also to be saved, but definitely the register contents is something to be saved. Okay, Abhishek is asking, what if whatever job is doing using the CPU is incomplete when its time finishes? Okay, that's a question which possibly tells me that one concept needs to be cleared. When its time finishes does not mean that the process will end now. Suppose you have written a program which total requires 5 seconds of CPU time. These 5 seconds will be given to it, but not continuously. So maybe 10 milliseconds will be given to it in one quantum. Then it will be switched. The context will be saved. Again, at some later point of time, it will be allocated the CPU. Again, it will run for maybe 10 milliseconds. So it will get multiple quantum. And if your job finally needs 5 seconds of CPU time, it will be given that. But that will not be continuous. So when its time finishes, don't think of that the process is that job is ending. Otherwise, there would be no need to even save the context. We are saving the context of a particular job because we know we have to resume it at some later point of time. Okay. So of course, the job is incomplete. That is why we are saving the context. Okay. Now Radhika is asking, with time, the number of jobs also change. So the switching time across jobs also vary with time. Yes, of course. So suppose you are at a particular time, there are only 5 jobs in the system. So then possibly each time quantum or each job would be given more time. On the other hand, maybe in office hours, there are 50 jobs in the system. So then each job would possibly be given less amount of time. So of course, if the number of jobs change, then how much time quantum is given to a job, that is also vary. Okay, I should not say that will vary, that may vary, but that will depend on the OS. Like the OS can decide maybe whether or not to vary. It might also be that the time quantum does not vary. But then yes, if there are 50 jobs in the system, that means each job will get its next time quantum after a longer duration of time. So the waiting time will increase. So maybe every job, when it is allocated the CPU, it will get maybe 5 milliseconds. But that 5 milliseconds will come after a longer duration if there are more jobs in the system. So Radhika, does that answer your question? Okay, and there is actually a reason for it. I'll just come to it. But I see some other questions. Let's see those. Pankaj, someone needs to save the context register values of the job before OS gets the CPU due to the hardware interrupt by the timer. Is that done by the timer too? Okay, great question. That's a very good question. No, the timer does not do that. But yes, so let's say the timer has come. The timer has raised an interrupt. The very first system routine or kernel routine which will start running will do this work of saving the context and register values. And often this will be done by hardware itself. You are right. So that's a very good question actually. So if the kernel has to run, then it has to use the same register, right? If the kernel has to run, it has to possibly use the same register values as the task A which was using. So how can it even run unless the context of job A is saved? So you are right. Even before the kernel starts running, someone has to do this. There will be a dedicated unit which will do it. And that unit actually is most possibly a hardware unit. Because you are right, until the context of job A is saved, no other program should be running because then the registers would be disturbed. Okay, Nandini has asked, does the OS decide how much of time will be allocated to a job, continuous time? Okay, good question, but this is very similar to Radhika's question. So I'll come back to it in a few minutes. Okay, so let us context switch this question for a minute. I'll be allocating myself to this question in a few minutes again. Let me go ahead a bit more, then I'll come back to that question and I can take further questions. Wait. So we are discussing about what are different needs for multitasking. So one thing is a hardware timer. The another thing is a scheduling algorithm. So see, suppose a context switch has occurred, as in job A was running till now, the timer had interrupted. Now the kernel is in charge. So context of A has been saved. Now the kernel is in charge. Now which task should the kernel allocate the CPU to? Maybe there are 49 other tasks in the system. Let's say there are 50 tasks in the system. So A was running. Out of those 50, one task has to be decided. It may be that out of those 50, some of the tasks are not ready for the CPU. Why can it happen? Some task is not ready for the CPU yet. Any idea? Any thoughts? Can it happen that there is a job in the system, but that job is not ready for the CPU? Can it happen? Exactly. Maybe that job is waiting for IO. Okay. Or yes, what Ayush is saying is right. That's a good point actually. So some job may be there which is waiting for IO, or maybe is waiting for another task to be completed first. So there is no point in allocating the CPU to that job. Right, so there is again a concept of which jobs are ready for the CPU. We will discuss this again in detail later, but it's good that you are understanding the concepts. So there is a concept that just because a job is in the system, a job is in the memory, does not mean that it is ready for the CPU. Maybe it is waiting for some IO or some other event. So the operating system does a lot of bookkeeping. It does a lot of accounting or bookkeeping. The operating system knows, or the kernel knows, which jobs are currently ready for the CPU and which jobs are not. And the kernel contains a scheduling algorithm. So the scheduling algorithm will consider only those jobs that are ready at this point of time and will allocate the CPU to one of those jobs. Okay, so again see, we are building a more complex system, but for that, we are building a much more efficient system, but for that we are having to keep track of many complexities. We needed a hardware timer. Now we need a hardware timer. Now we are talking about, we have to do some bookkeeping also to remember which jobs are ready, which jobs are not. Then we need a scheduling algorithm to allocate the CPU to one job which is ready. Okay, now the next point. This point is important, and actually this point is relevant to the questions that Radhika and Nandini asked. So see, how frequently should we switch jobs from one to another? I said 5 milliseconds. Okay, so now suppose there are many jobs in the system. So then should we reduce 5 milliseconds to 1 millisecond? Should the operating system decide that instead of 5 milliseconds, let's assign let's allocate the CPU to a job only for 1 millisecond, so that every 1 millisecond the kernel will try to switch the job. Do you think it? Do you so see why the question is arising is clear. Maybe so let's assume a hypothetical scenario that at one point the system was quite less loaded. There were only 10 jobs in the system. Then we decided to do it 5 milliseconds. So we decided to allocate the CPU to a job for 5 milliseconds each. Now there are 50 jobs in the system. So now should we decide to allocate the CPU for 1 millisecond only to each job? Should we decide, or do you think that can lead to some other problem? Hanging. Okay, let's not talk about hanging here. Hanging can happen due to many different situations. So let's not talk about hanging here. Yes, what Ayud is saying is, Ayud and Mukul, what they are saying is what is also written in this slide. See, every time one job has to be switched out and another job has to be allocated the CPU, several extra work needs to be done. All these context needs to be saved. The kernel has to run for some time. The scheduling algorithm has to run. So all these extra work is not helping any of those processes, right? All these extra work is not actually helping any of those processes. This is just extra bookkeeping that we are doing. So maybe switching from one job to another every 1 millisecond may be too much of a overhead, because every 1 millisecond then the scheduling algorithm has to be called, the kernel has to run for some time, register values need to be saved, and so on. Right. So typically the OS, or typically this time quantum that is allocated to a job will not reduce. Right. So because we would not like to take too much overhead. We would not like to do context switching 1,000 times in a second, because then the overhead would be too much. Therefore, so now I hope Nandini and who asked? So the question that Nandini asked and Radhika I think also asked. So now I am answering that in a bit more detail, that maybe the OS does not need to decide, or possibly the OS will not decide to reduce the time quantum. Rather, the time quantum will remain the same only if there are more jobs in the system. A particular job will get its next time quantum after a longer duration of time. Because let's think of a round robin scheduling kind of thing. So if task A has been given one time quantum, after that it will receive the next time quantum only when all other ready processes have been given one time call. It need not be always that, but I am just taking an example, right? So basically see, and it's not so, and see the situation is completely dynamic. Which process is ready for the processor, that also is changing with time. Suppose there was a process, suppose there was a process B which was waiting for IO, but that IO got completed. So now B actually may be ready for the CPU. So then the scheduler will take into account that whether B is ready for the CPU. And if so, it is a candidate for allocating the CPU. Okay. So the whole situation is dynamic. Every time the scheduler runs, so there has been a context switch. Every time the scheduler is running now. The scheduler has to decide, he has to check which all processes are ready, and out of those it assigns one job the CPU. Okay. And a related concept is this concept of CPU burst and IO burst. See, as we discussed, there is an overhead associated with context switch. So, by the way, this task of switching the CPU from one job to another is called context switch. Okay. And as we know, this involves many steps. Say A was running and the context needs to be switched to B. So first someone will have to save the context of A. Then the kernel will run. The scheduler will run. Scheduler will decide the scheduler knows which other jobs are ready. Out of those jobs which are ready for the CPU, it allocates the CPU to one job. Then that job starts running. So this whole process is called context switching. And we discussed that there is this overhead of context switching, a lot of extra work has to be done. So we would not like to have that very frequently. And this brings us to the concept of CPU burst and IO burst. So the idea is this: once the CPU has been allocated to a process, we would like it to do a lot of CPU operations in this amount of time. Ideally, see, think about this. Suppose you have a program, you have a task, you have written that task. Every time the CPU is allocated to your task, your program, it just does 2 or 3 CPU operations and then asks for IO. So again, it has to be switched out. Again, at some later point of time, it is allocated the CPU. Again, it does 2 or 3 CPU operations and then again asks for IO. Again, it has to be switched out. So this is very inefficient. First of all, too many context switches are occurring. So it's inefficient for everyone because of the context switch overhead. Second, with respect to your task also, it is wasting the resources that it is getting. So it is being allocated to CPU, but it is just doing 2 or 3 CPU operations and then asking for IO. So your program is also getting delayed too much. A better design would be if your program is written such that once it gets the CPU, it does a lot of operations on the CPU. And then it asks for IO maybe. And when it asks for IO also, it does a lot of IO. Right, so that's the concept of CPU burst and IO burst. If you get some resource, utilize it as much as possible. Okay. So lots of CPU operations or lots of IO operations in one go, so that the context switches are minimized. Any questions? No. Okay, at this point, let me ask one last question for today. This concept of CPU burst and IO burst. Do you keep this in mind when writing a C program? Suppose what I mean is, suppose your program has to do a lot of print statements. Do you keep in mind to print everything together or print many things together, etc.? Yeah, the honest answer is no. No, not only you. I mean, don't think I'm trying to say that you all are bad programmers. No, no one keeps this in mind. So what do you think happens? So we often write programs such that in every iteration of a loop, we print out one variable. Let's say we have a loop for I equal to 0, I less than 1000, I plus plus. In every iteration of this loop, we are printing out the value of one variable x. So this, according to, if the CPU burst, IO burst concept is there, this is not a very good design, because every iteration, maybe you are doing several you are doing several CPU operations and printing out one value. That's a bad way of writing. Okay. So what happens? What do you think is done? We don't take care of it, but does someone take care of it? What do you think? Okay, I'm getting some answers. Someone said rearrangement of instructions, Atharva. Someone said flush, Shubham. Mukul says don't print instantly, keep in buffer, etc. Excellent. Is something like this done? Do any one of you know? Maybe just if you know, you can unmute yourself and say, because the class is about to end. So, say Mukul, any idea? Does this happen? Don't print instantly, keep in buffer. Does this happen? Mukul or Shubham?
Sir, as far as I know, while printing to std out, we keep them in buffer, and there is actually a function called fflush that flushes the buffer and prints out in the screen.
Excellent. Yes, that's exactly the case. Every time you put a print statement, the print is not carried out or may not be carried out instantly. There is usually a buffer. You may have heard of things like std in, std out, std err. So, okay, those concepts are a bit different, but yes, usually your program is not directly reading from the keyboard or not directly printing to the screen. There is a buffer. When your program is saying print, what you are asking it to print gets stored in that output buffer. Again, maybe next iteration, you ask to print something that is stored in the IO buffer. I mean, the output buffer. Again, next iteration, you ask to print something that is stored in the output buffer and so on. At some point, it will be decided to empty all those contents of the buffer to the terminal. When will that happen? That is a difficult question to answer. One thing it can happen is the buffer is getting full. Right, so of course the buffer is not unlimited. So maybe you are printing a lot and the buffer is getting full. So therefore at some point IO will have to be done. But that's the whole idea. When you do IO, do a lot of IO. That's the IO burst. Okay. But also the designers of C programming language also have given us this option that you can force printing right now. So you can force output. You can force the output of whatever is contained in that buffer right now. And for that, there are some functions called fflush. So you can do fflush of std out, etc. So that kind of you are immediately asking for an print, even though it is not efficient, but for some reason you want the print exactly to happen right now. So C has given us this facility or mechanism. But in general, do not think that whenever you ask something to be printed, that is printed. Let me ask, okay, have any of you felt this? Have any of you experienced anything which makes you also feel that this happens? You have asked to print something and that is not printed instantaneously. Have any of you experienced something like this?
Yes, so sometimes it has happened, like there is a segfault coming and there should have been something printed before, but that doesn't get printed.
Excellent. Yes, that is the one point where we understand that something like this happens. So suppose you had given a print statement. In the next line, a segmentation fault happened. So that means the previous print statement should have been executed, right? But it did not print anything. That is exactly what the reason. The print is not carried out instantaneously. The value is saved in some buffer, And then before that buffer was printed out, your program did something illegal. So it was terminated by the kernel. So that buffer was not printed. Okay. So this sometimes happens, especially when there is a segmentation fault. So sometimes a print statement even before that line where that segmentation fault occurred, that print statement may not have printed till now. Because that value was written in a buffer, even before that buffer could be written out, your program did something illegal, so it was stopped. Okay. Fine then. Okay, so it's good that you are, as I said, as we discuss concepts in this operating system class, try to connect these to experiences that you have got in your while you are programming. We have done a lot of programming till now, right from PDS. You will see that some of the experiences that you have got till now can actually be correlated with what we are discussing right now. Fine, so let's end this class here. We will continue tomorrow.